Hello, everyone. My name is Hong Yingao from Tech Laboratory of Tianjin University. Today the topic of my presentation is XShot, lightweight link failure localization used across the probing cycles in SDN. Okay, let's start the topic. Today, the communication networks grow rapidly in scale. It often heals up to 10,000 of network devices and even more links. This will cause that the network failures become very common. For example, failure stop failures and partial failures. The partial failures and like a faulty link dropping packets randomly. These failures often cause severe service outages, and these outages often take hours or more to restore and bring huge economic losses and labor consumptions. Therefore, timely failure detection and localization is very critical. The exciting detection and localization tools rely on network monitoring. The monitoring approaches can be divided into two parts, that is passive monitoring and active probing. The passive monitoring is using readily available metrics to generate failure alarms, but the downside is that alarm signals are often missed, hence, the passive monitoring often introduces many false alarms and turns failure localization into a long-time process. But the active probing is to inject probing packets to monitor the network status. But it cannot provide accurate failure predictions, just because the routing in traditional networks is often unknown. Fortunately, SDN, that is a software-defined network, opens up opportunities for that problem. It decomposes the control plane from the data plane, and it routes packets on predefined paths, like this. The profiled paths make it possible to locate the exact position of failure efficiently. Connectivity verification methods is often used in SDN network. It is measures the up or down state of a path according to the receiving state of probing packets. Moreover, richer link metrics also can be further derived through end-to-end performing measurements. Although this method is very effective for the detection and localization in SDN, but it cannot distinguish fail stop and partial failures. Moreover, it incurs high costs, including additional hardware monitors, many probing packets, and forwarding routes, and long probing times. Here, the probing packets impose a large communication load, and the forwarding routes often take expensive resources of TCAM. Therefore, we aim to pinpoint the exact faulty links in SDN in a more lightweight and quick manner. The first step is to save costs. That is to reduce the number of probing packets and forwarding routes, and we don't want to need any more additional hardware monitors. And the other aim is to distinguish field stop and partition failures. There are two major challenges faced with us. That is, the first is how to formulate the probing costs in terms of packets and routes. That means probing packets and forwarding routes often increase over the number of probing passes. To minimize the cost, the probing passes should be crafted carefully. And the second challenge is how to identify partition failures from noisy measurements. Given the probing passes, it is often noisy. It is the measured metrics are often noisy. It is very difficult to recognize partial failures from these noises. Therefore, how to find partition failures from these noises is a very important problem. To solve the challenges, we present XShot. It is a quick and lightweight failure localization system in SDN. It is mainly based on cross verification method. The cross verification is a cross probing based link failure localization method in SDN, and we also introduce an ILP model to minimize the number and the length of probing passes. The last is ADW donut. This donut is an improvement of machine learning algorithm. It is used to learn. To identify partition failures from noisy measurements. What's cross verification? It is a method to localize the faulty link within just one round shot across. That means each link failure corresponds to one and only one binary code, and the code is defined based on the probing results of cross passes. For example, this is a probing solution. This is a probing solution for an SDN network. As we can see, there are 5 probing passes. That is probing cycles with controller C and the only monitor, and each link has a unique 5-bit failure code. Like the link S2 to S3, its failure code is 00110 because it is traversed by the path 3 and path 4. However, there are some limitations of in the existing cross verification. That is, in all optical networks, a node can only be traversed at most once by each probing cycle, and the same with the link. This is because optical signals of the same wavelengths can only be transmitted in one direction on each link. These limitations often cause failure localization problem. For example, there are two network structures, one cut and two cut structure. In the one cut structure, there are no probing cycle, and in the two cut structure, there are only one probing cycle. But all links in the two structures cannot be distinguished from each other. Therefore, our cross verification is improved based the existing method. In SDN networks, we allow a node traversed multi times by each probing cycle. There knows that a link only can be traversed at most once in either direction by each probing cycle. This is an example network with one cut and two cut links. We can see in this table all the links there is each link have a unique binary code. This means all links in this network topology can be distinguished from each other. The XShot design is as follows. XShot consists of three components. That is probing path planning, active probing, and data analysis. Probing path is probing path planning. Given the network topology, this module generates a probing solution consists of probing paths and failure codes by LLP model. The LLP model is formulated based on the cross verification. The objective is this. Consists of two parts. That is C packet is the probing packet cost, and the C row is the forwarding row cost. Omega is weight, and it is often larger than 1. Like this network, we use ILP model to generate a probing solution. It is comprised with 5 probing passes and 15 failure codes for each link. And in this table, each link has a unique failure code. The second module is active probing. It often installs the forwarding rules on switches according to the probing passes, and then sends packets along them to measure the end-to-end latency. This table is the forwarding rules for path 1. That is the green line. It consists of 2 paths. that is match fields and actions. This is the format of the probing packets. Here, the VLAN ID is very important. It is the path ID using to distinguish the packets of different passes, and the data is to record the sending time of the packet. Data analysis is the last module. It collects the mirrored latency, detects the path standards, use the surprised learning algorithms, and pinpoint the exact faulting link according to the unique binary code. To detect the partial failure, the XShot choose donut an unsupervised anomaly detection algorithm based on VAE, but unfortunately we find transient unexpected fluctuations exist in the mirrored data. Like this, the spikes in the picture affect the detection accuracy. And we also found the CPU uses have the same frequency with latency. Hence, we introduce an accelerated detection window ADW into donut, that is ADW donut. The first step of ADW donut is to send a certain number of additional probing packets in a higher frequency upon detecting an anomaly. And then if there are more detected anomaly in the ADW, the detection result of donut is true positive. Otherwise the result is false positive. The evaluation. This is the evaluation part. This our experiment environment and compared approaches. And we have 3 main metrics. This result is the number of probing packets and forwarding route. In this picture, we can in 79.37% of topologies, XShot requires 9.63% less number of probing packets than logic ring. And in terms of the number of forwarding routes, XShot and logical ring requires roughly the same number. Which commonly copy less than 0.1% of TCAM resources. And this results is for the failure detection performance. From this picture, we can see that due to the fluctuation in mirrored latency, ADW donut yields less for positive result and have a better detection precision. And ADW donut increase the precision to more than 914% and keeps the recall more than 18%. This is overhead. XShot increases the CPU uses by less than 3 point compared with the XShot not working situation. That is interval equals INF. In case of challenges of the number of probing packets, the CPU uses has barely changes. And in the terms of in terms of my memory usage, the controller consumes only around 0.7% memory, little of which is caused by XShot. And this is the conclusion. XShot is a quick and lightweight link failure localization system in SDN. It pinpoints the exact faulty link within just one road short of probing, and it also reduces the number of probing packets and forwarding rules. And also identifies the partial failures and the detection precision of more than 94%. Okay, that's all my presentation. Thank you for listening.